Okay, right. Yeah, well, that's interesting. We've got to, I think we're going to swap to an official IBIPSA Zoom account for these in future rather than the UCL one. So we'll see how that goes. Right, I'm just going to start, okay?
Sure.
Hi, everybody. Welcome. I'm just going to give it a few more minutes. There's still people coming in, so while they're still popping in, we'll just wait for them. So I'm just going to, I'm going to launch a poll just now. So I've got 3 quick questions for everybody, and maybe while we're just waiting for a few more people to join, you can have a look at those questions. If you've joined one of these webinars before, you'll be familiar with this. It's our bit of market research where I try to find out who you are, where you're from, and what you'd like to see in future webinars. So do please pop that in. And thank you to everybody who's answering that at the moment. I'm going to see if I can go back to my previous slide. Which seems to have popped off, but there we go. So welcome to this simulation best practice webinar, where I'm delighted to introduce Nishesh Jain, who's going to be presenting a webinar about design stage performance modelling, and he'll talk a little bit about exactly who this webinar is for as well. So it is part of a series that's aimed at those who are using simulation in their working life, and those who are new to simulation, rather than some of the more academic series that we run. And it's all part of the IBIPSA Education Committee purpose, which again, you'll be familiar with if you've been to one of these webinars before. But the committee's role is to identify education and training needs, to develop and encourage and coordinate new educational materials and methods. And what's really important, I think, is that we offer training sessions to non-members as well as to members. So you don't have to be an IBIPSA member in order to join these webinars, but we'd love it if you joined us afterwards, of course. So the format of this morning, this lunchtime session, for those of you in the UK, is going to be a quick poll. Then I'll hand over to Nishesh to do his presentation. I'd ask you, please, if you have any questions as he's going through his presentation, to put them into the question and answer box at the bottom of your screen, and I'll put them to Nishesh at the end of this. And then after we've done your questions and answers, we'll end with a little bit of information about webinars that are coming up next. So do look out for that and get your diaries out ready for booking. So without further ado, Nishesh, I'd like to hand over to you. So if you could just unmute and share your screen.
Hello everyone. Um, so, Welcome to this webinar. Let me introduce myself. My name is Nishesh Chen. I am, as the screen description says, a research fellow at University College London, and I also work with Design Builder software and on my area. I'm into modeling for about a decade now, trying to see what the learning experiences, etc., for people have been through this journey, and I'm trying to compile things for a focus on what is performance modeling, what the basics of those are, and I have been involved in some industry publications on related things, specifically in the UK. So hopefully you find the things here informative. So the background stuff is like modeling right now. I'm seeing the trend, it's in use of modeling has increased significantly over the time I have been involved with it. And now more and more across the world, it's becoming part of regulatory compliance calculations. So therefore, it's something which is really picking up. So in this webinar, I'll discuss how to undertake better informed calculations for energy performance projections in buildings. And my webinar is, or the way I'm approaching this is targeted at early career sort of modelers, performance modelers. However, if you are an experienced or what proverbial good modeler, then you can also stay here for a while, see what is there, and because from I can benefit from your feedback on this presentation. So yeah, please do put some feedback, questions, etc. In the question section on this. Either ways, if you are early career or you have some more nice insights to contribute to while I'm progressing. So in this webinar, um, I will start with exploring the use of performance modeling in building procurement process and explore the various modeling methods, their needs, requirements, and applications. We will look into a structured modeling workflow for creating better and more accurate performance models, and basically following the steps in CIPC TM54, we'll develop a early stage model, and then the steps might be similar to other good practice modeling guidance that is used globally. So while my focus is on TM54 and its process, the key concepts for your protocol will be similar to guides such as Neighbors or ASHRAE 209. We'll also be looking at ways to present results for better and cleaner communication about projected performance for more informed design decisions. And finally, we review modeling done at advanced design stages with detailed systems and controls, and also look at the role of building performance modeling in performance evaluations after occupancy. I'll try not to reinvent the wheel here, but rather my content for this presentation is to signpost to already existing information in a threaded manner. So performance estimates of energy use at design stage can allow designers, building owners, prospective occupiers to understand where and how energy is likely to be used in the building. It builds realistic expectations about performance of the building and allows designers to understand which performance measures have the greatest impact on energy use, therefore informing the energy end use targets, which can be compared with operational data to identify opportunities for tuning and optimizing the building in use. The building procurement process goes through multiple phases. So the key tasks in a procurement of a building starts with project conceptualization and planning, which moves then to the design development phase. Subsequently, the building is constructed and the handover happens. And then there is a stage which is post-occupancy, completion and operations and maintenance stage that comes. So typical role of modeling at the initial planning stage related to energy and environmental performance is to determine the project targets and benchmarks that can be achieved. Therefore, what sets the realistic expectations? Beyond that, at the planning stage, compliance-related modeling is also undertaken, which may be extended into design stages as well. Most of the modeling we typically do, that is performance modeling, which is the key topic today, happens during the design stages. And as the design evolves, the model evolves and gets customized to the project specific details. In this webinar, we are focusing on this type of performance projection modeling. Beyond this, into the construction and handover stages, value engineering often drives changes in building design and specifications. Therefore, upon handover, the model should be updated so that it aligns with the as-built building as much as possible. Ideally, at this stage, the model should show the targets for the energy and comfort metrics are easily achievable. The role of modeling necessarily does not stop when the building is occupied. Calibrated models can be used to help understand underlying performance issues and give insights into operational inefficiencies along with pinpointing their root causes. This is especially useful during the initial years of operation when building and systems are fine-tuned. This is how the tasks link to the well-known project type of stages. And I have taken these stage markers from REBA project stages, but I've assumed it's similar in most places, AIA or with any other bodies. The key guidance on each of these modeling types are discussed here, which have here can be found in multiple industry guidance documents, such as there are guides and documents for benchmarking and also for regulatory compliance modeling. These guides for compliance or benchmark typically vary by country or region. So, they would be there, but different places would have different versions, iterations of those. However, more broadly applicable guidance also exists and is typically used for performance modeling at design stages or for post-occupancy evaluations. The key issues that affect modeling and should be taken care of by modelers are, firstly, not to use the wrong type of modeling. For example, compliance models are created for comparative assessments and benchmarking. However, it is commonplace to interpret the results from compliance models mistakenly as predictors of actual energy use. It has to be remembered that the compliance models are hugely simplified and their purpose is different, especially when you compare them to full performance modeling. Another issue is input assumptions. Generic design and operational assumptions are often used in compliance modeling. However, in performance modeling, it is essential that we use building specific model data as much as possible. Further, a slightly less intuitive issue that modelers often ignore is the deterministic approach to present modeling results. When modeling at design stages, there is a common tendency to project energy use as a fixed number without assessing or looking at the likelihood of achieving it. As good practice, multiple scenarios of high energy, low energy, medium energy options should be explored. Furthermore, as the design goes through the construction and until the handover stages, any changes in design or proposed operations generally occur. Such changes to operating hours or such as they are product substitutions during value engineering. Therefore, at relevant stages, especially at handover, the model and projected performance should be updated. Finally, poor commissioning of the actual building can also be a cause of discrepancy between ideal performance projected by your models compared to what actually happens in buildings. So another flag to be aware of. Our focus in this webinar is performance modeling, and these are typical guides that are used in the industry in some places, such as ASHRAE Standard 209 or Neighbors Design for Performance Guide and CIPSE TM54. There are likely to be other similar guides available globally that provide clearer guidance on how to evaluate operational energy use accurately at the design stage. These documents are complementary, and I was involved in the recent update to the CIPSE TM54 document. So I'm using that as a basis to illustrate what these guides usually contain and the modeling processes that follow. So TM54 or similar guidance on provides predictive energy modeling advice for design stage modeling. It explains the importance of accurately estimating the operating hours and likely occupancy levels. And it emphasizes on accounting of all regulated and unregulated end uses within the building energy totals. Practical recommendations for good modeling which are covered in these documents can be categorized into two parts. Firstly, recommendations for better calculations, and then recommendations for better presentations and explanation of results. By better calculations, I mean is that the requirement of use of appropriate simulation software and use of project-specific assumptions. The second part is to present the calculated results in a manner that gives holistic understanding to all the stakeholders. This is done by not just presenting the results as they are, as deterministic values, but also via scenario analysis, sensitivity analysis, and comparing performance against other similar buildings, and that is benchmarking. So this is the step-by-step methodology that is there in TM54 document, which I'm using in this webinar as well. But for simplicity and generalization, I've divided it into 6 parts. The first part is more strategic and focuses on using the right modeling approach and detail. The next 3 parts relate to developing a model with correct geometry, model data, and HVAC systems. This is effectively our baseline or starting model of the modeling process, upon which further steps are built for better performance assessment and communication. The communication starts with projection of the actual results as well as determining the uncertainty in those results, and then also checking model's robustness by undertaking scenario and sensitivity testing. The process also compares the projected energy use against project targets and industry benchmarks. So the initial decision before we start modeling is what type of modeling do you need for a project. There are different levels of modeling depending on the need and complexity of the project. So there is quasi-steady state modeling. There are dynamic simulation modeling options. Steady state modeling, which such as using spreadsheets, PHPP, which is used in passive house design, although relatively simple in nature, can be very useful tools for simple projects where the heating demand drives the space loads and the variabilities in the building operations is less. They can be, however, less reliable for bigger projects with varying thermal loads, complex controls, and especially when cooling demand is significant. Dynamic simulation models, in theory, provide a better estimate of energy use compared to steady state calculations, as they take into account more of the complexities of variation in energy use across time and interactions between different parts of a building system. We'll be focusing on dynamic simulations in as modeling approach in this session. So I'll just quickly review the model I'm gonna demonstrate. It's more like a placeholder sort of model so that we can look at it. So, switch it on. Okay, so this is a student accommodation block model, quick shoebox type model which I have created. The building has 8 ensuite flats, 4 on each floor. The ground floor has a kitchen, and then the upper floor block is identical, except that it has a common roof instead of the kitchen. There is a building on the east adjacent to the block, which will shade and reflect our building. The geometry is here. The model data itself is defined on the tabs above, which we will review as we go along through the modeling steps. Step 1 now in modeling itself is to create the accurate geometry and define the correct location details. Geometry forms the basis from which all future calculations are undertaken. Its accuracy and quality will therefore affect the accuracy of future model outputs. Many factors should be considered when generating a model, such as keeping it simple and define opaque and non-opaque fabric properties correctly, including minor details such as thermal bridging and window frame effects. You need to apply correct shading as louvers, overhangs, canopies, and the surrounding buildings and trees. Also ensure that you correctly configure all the zones and zone groups, etc. Further guidance on constructing a suitable model are available in these guides that I mentioned earlier, and they list down key things to remember while you do your modeling. An important aspect with geometry creation and general modeling is how to work with large models. Dynamic simulation tools like Design Builder, which I showed right just now, can be used to successfully model and simulate very large buildings, over 2000 zones, and with huge floor areas. So this knowledge base article provides great tips on how to maximize productivity in case of large models. The link is here, but I'll show you how to access this and other resources on this type of guidance at the end, towards the end of the webinar. Now back to geometry and location. So now location is the next aspect of the initial model setup. This governs key factors, including the weather data and parameters for heating and cooling design calculations. So an appropriate weather file specific to your building location should be used. For building specific projections, if more accurate weather data is available for a nearer weather station in a climatically similar location, then you should use that in the baseline projections. There are various different types of weather files, and when you are doing performance calculations, then you would most likely be using typical year data rather than design year data. And related to the guidance on weather data selection, I can point you to this webinar, which was done recently on a new weather data service by Design Builder, but it covers at length different types of weather files, what weather data to use when, and then how to actually obtain them from the climate analytics platform. And another weather data related resource to point out uh, is on the same webinar space. There's another one, which is a roundtable discussion between Drew Crawley, Joe Wang, and Andy Tyndale, where they talk about all things weather and issues, etc., including weather tools such as climate1building.org, Whitebox Technologies, and Design Builder Climate Analytics. So now back to our workflow itself. So we have done the geometry and location setup. Now the next step is operating hours and occupancy. It's important that correct zoning and activities are defined for a model. The operating hours and occupancy schedules should be set as accurately as possible. When we start modeling, we use typical operational profiles defined in common standards for occupancy, loads, operation profiles of various things, such as here are the schedules for a student accommodation bedroom space from a typical database, which assumes reasonably that there is occupancy during evenings and the student accommodation is having no occupancy during the day when students are in lectures. So in most scenarios, these operational assumptions feel realistic. However, when developing a model, every assumption should be questioned and verified, specifically maybe discussing with the stakeholders and client. Because contrasting this typical operational assumption against monitored electricity load from a couple of student residences at UCL provides an interesting insight into the student building's operational trends. What is clearly visible here is that the assumed slump in usage during the day in a typical schedule, which is on your left, is not evident in the student accommodations as such. No, and this data is before the pandemic times. Therefore, what we conclude is that even though projections and projects which are in this, which are for the same category, due to contextual reasons, might have different operations. A structured discussion with the client is therefore useful in these cases, typically to understand occupancy patterns, operating hours, along the way, along with the way the building would be managed eventually. And ideally, this should be backed up by data rather than estimates. So for our model, let's do the more realistic customizations for the occupancy inputs. So in the model, relevant activities have been assigned for various space types for bathroom, circulation, bedrooms, etc. And as I highlighted in the slides, that typical data may not be suitable for the occupancy and operating hours for this building. For example, uh, right now, our flat has a default occupancy density of 0.12 people per meter square. And if I look at the area of going to a flat, then it's about, say, this one is 35 square meters. So full occupancy for a flat like this with these trends would actually be 4 people. However, in our case, our flat is single occupancy. So therefore, I need to make the numbers more realistic and correct to my thing. So I'll just change the occupancy method, and instead of number of people, now number of people, I'll change it from something, I'll change it to 1 person. And similarly, the operating schedule itself, I can change it to, so this is the current one being used. Let me see. Uh, So I've created a few new schedules in here, so I can select that and I can show you. So this is accommodating the kind of slight use of the spaces which are there. So select that. So that ensures that our um, occupancy, etc., is more realistic. The next few steps require modifications to other loads and their schedules, such as for lighting, equipment, and other systems. So what we'll do is, instead of making the changes one by one, I'll quickly make some more context related changes. Uh, so this is bulk editing system I'm going to use to make the change. So, for example, just for simplicity's sake, I'll try and only do the changes in the bedrooms. So you can see selected all the bedrooms and number of people has been changed to one, as well as the schedule for occupancy is coming out correctly. Now, assuming that the set points of for heating set here are too low, I can select them because I think realistically they will be maintained at higher temperatures. So I will make them correct. 22, this becomes 16. Can also change the equipment in this rooms to 8 watts per meter square. And also I can change the equipment schedule to a new one which I have created. So besides this, I have also already updated the lighting schedule, auxiliary energy loads, hot water, as well as other schedules in the model. So for an actual project, you will go into much more detail in customizing the inputs, but this is a demonstration, so this much is sufficient. But the whole idea is to go through everything and modify that. Um, so after this, let's go back to our slide and see what the next step is. So after adding all the data itself for the baseline projections, the last item is HVAC system design. So depending on the design stage and the complexity of building systems and their controls, a simplified template-based HVAC modeling or a detailed HVAC modeling can be done. Typically in early design stages, simple HVAC modeling is okay as it uses plant loads and seasonal COP values to calculate HVAC energy use. However, at more advanced stages where complex systems and controls are being modeled, then component level modeling with performance curves for HVAC energy calculations is preferred. Typically, as the design evolves, your model will also evolve with these details wherever necessary. In an earlier webinar on one of the previous ones available on this webinars page, actually shows you how you can work with a simple HVAC system in an initial model and then switch to detailed HVAC modeling in the same model as project evolves and design decisions evolve. So you can access the recording of the webinar from the page here. Again, I'll show you how to access it later again as well. So back to our model and let's quickly review the final piece then on the HVAC system. So in this model, I am modeling a simple HVAC system and I have preset most of the inputs in this model. So the HVAC system is a VRF system providing heating and cooling. And then there is also natural ventilation for fresh air supply. Once the model has reached at this stage where the HVAC and geometry, location, model data, everything is defined as per the design intents and feedback, our baseline model is complete and you can run the simulation. So now it's complete and you can do a simulation run to check the results. So I'm doing it for a full year and I'm requesting annual year totals. In this simulation, I'm only interested in the fuel breakdown at an annual level. So I did not ask for more detailed outputs, such as what's happening with internal gains or various surface level outputs, comfort, environmental results, etc., at much higher granularity, like hourly, sub-hourly. I would have done that if I was actually analyzing uh, the building performance in more detail and for a real project. And also it's a good practice to do proper QA checks of your models before you embark on final runs. I have skipped this to save time, but this can be the type of QA checks you can do is by simulating short time periods at high time frequency, like hourly or sub-hourly, to ensure that the systems and operations are running as they should. This type of QA checking and sanity checking is a very essential step for modeling. So simulation is complete. I'll look at the fuel breakdown to see how much energy is being consumed. So just look at graphing table and I'll normalize it by the area. So this is the projected energy use based on reasonably realistic operating conditions for our model and represents the baseline energy use of our project. I'll now move to the slides and we will discuss these results. So the energy use projection calculated in accordance with TM54 guidelines, the way we have developed the model, with building specific model inputs, results in a projection of 78 kilowatt hour per meter square per annum as the energy use intensity. This projection accounts for all anticipated energy uses in the building rather than just regulatory loads or the central plant or equipment. This provides a holistic view of the performance. Now moving on to the next part, that is presentation of the results that account for uncertainty. So we have got a deterministic answer now. Let's see how we can better present our model findings. So after initial baseline projection is done, sensitivity analysis and scenario testing should be done at appropriate stages to understand the factors that are likely to have the greatest impact on the energy consumption of the building, presenting the results as a range. For that, you would have to define normally via interviews with stakeholders, key parameters that might change between the design and operation stages, such as HVAC system specifications or operation protocols or occupancy patterns, etc. So why do we need to look at uncertainty? Models are created using assumptions. And as design evolves, some of these assumptions become more certain, but others, specifically those related to operations and occupant behavior, will remain uncertain. This means that there will always be a difference between a building's predicted performance and how the building is actually likely to operate. Additionally, designs often go through changes such as value engineering. Therefore, using these tests, we can gain an understanding of how important some of these design changes are. And consequently, we can make stakeholders aware of the need to safeguard the key energy conservation measures. Sensitivity analysis itself is a study of how variation in model outputs can be attributed to the uncertainties in the inputs. Thus, it helps to identify what are the most important factors and variables in a model So how to go about a sensitivity analysis would be that a basic sensitivity test is a simple approach of making some iterative changes, such as for weather or occupancy related factors, and checking the impact on the results. The magnitude of change can tell what the impact is. For example, in this graph, we can see that the calculation, where each calculation is having a parameter changed, then the sensitivity of energy used to operating hours is more than that what is due to efficiency improvement of the system. Therefore, we can see that which occupancy related parameter in this instance is more important factor than the system efficiency. A more structured way of assessing sensitivity is to do a multi-parameter analysis. Multi-parameter analysis is a holistic analysis and allows you to determine the combined effect of changing multiple inputs at the same time, because combined effect may not be directly equivalent to sum of its parts, and some of the variables might cross compensate each other. With this type of study, you can identify and rank inputs in terms of their importance. And this parametric approach, which is, for example, in design builder, it is already integrated, is especially useful when quantifying risks in projects procured under performance contract, where you need much more accuracy because it's a contractual obligation to achieve performance targets. So there is a this uncertainty and sensitivity analysis webinar actually looks at a quantified risk assessment reporting using sensitivity analysis to measure and manage risks associated with achieving performance targets. There is a webinar, it focuses on a real project which is under energy performance contracting to achieve a state-of-the-art rating in the UK. So the use of sensitivity analysis is shown in great detail in this application. Scenario testing is a slightly different concept. Scenario testing aims to quantify the total variability in the calculations due to all the uncertainties in the model inputs, effectively uncertainty analysis, quantification. So typically, to show results probabilistically, 4 scenarios can be communicated to the clients. First is a mid-range scenario, which is effectively our baseline case. This is the best estimate of energy use based on most reasonable assumptions for the building operations, system efficiencies, controls, management regimes, which we have just done. Then you can have a high-end and low-end scenario, which represents the likely range of output uncertainty. That is the likely energy use variation based on reasonable variations in things such as building occupancy or operations. And finally, there is a worst case scenario where modeler would assume high degree of mismanagement and inefficiencies in building construction and operation. The intent of the worst case scenario is to inform the project team about the potential negative impact of their actions. So while the high end represents the realistic high energy use which the building can have, the worst case is the worst possible performance the building will have due to mismanagement, etc. So the factors you would consider in developing these different scenarios would be variables which have strong influence on the results as identified by sensitivity analysis, especially if they vary between a very wide range, or if they are subject to very low confidence or certainty at the stage when the modeling is being done. You can also consider having variables for controls for things such as heating or cooling, or when the windows are open. Occupancy and hours of operation of building are a very important option to consider. Internal gains is another variable, such as equipment lighting, which should be considered. Then scenarios exploring different system efficiencies for plant equipment, and weather-based scenarios should also be considered. by using different weather data such as cold winter, hot summer, or future climate. Management actions that may impact the running of the building and services, project specific things can be also considered. And the important thing here is to note is that these scenarios which you would test is based on modeler's own judgment and they will differ per project. So, but we need to factor those in. A quick scenario analysis was done for the demonstration model by modifying these parameters which you see in the table. And values were used under low, medium, and high energy options. The medium scenario is the central estimate, which is our baseline model, and high and low are the probable ranges within which those items would vary. These inputs could relate to impact of building controls and building management, like these two items, or their occupancy and occupant related factors. There are typical variations in internal gains, range of system efficiencies, and some weather scenario variations. Simulations were run with these three set of settings to create the simulation results. And the result plotted shows the annual error range, that is the low end, mid range, and high end scenario. And the actual performance of the building is most likely to be somewhere between these numbers, somewhere between 55 and 105 is the actual energy use of the building, not really the 78 number we came up with. Scenario analysis can also be plotted as box plots for different end uses separately. This graph, you can see the bar shows the median value and the error line is the high and low range estimate for each of the end users. So the final part of TM54 is to compare and the calculated performance against benchmarks based on actual building data. So just plotted for our demonstration building, the performance against the SIPC's good practice benchmark. And what you can interpret is that the building design projection along with its high-end scenario is within the limit of the good practice benchmark. So let's review the performance projection type of modeling, which we looked at right now. So at early stages, simulations can be used to test and refine operations and energy targets under a range of real-world scenarios using initial performance models with simple HVAC, as we just did. As the design progresses, areas where detailed HVAC modeling is particularly beneficial include a greater ability to optimize air side modeling of mechanical ventilation systems and water side modeling of heating and cooling systems, including heat recovery. HVAC modeling is also powerful for simulating heating and cooling plant, fan, and pumps performances in more detail, plus the testing of control options. Detailed HVAC modeling provides a detailed representation of system operations for calculating HVAC energy use. It incorporates each component within the system using manufacturer information about part load performance to describe the performance of each component. Controls within the simulation reflect the controls proposed in the design. The detailed HVAC model is bespoke to the project. This, however, is an approach that would more or less give a better result, but it's debatable that modeling HVAC systems in more detail at design stages actually adds or reduces accuracy and certainty of the results when compared to the simplified ideal loads based approach. In my opinion, the decision of whether to use simple HVAC or detailed HVAC should be based on the stage of building procurement at which the model is being created or used. In the earliest stages of design, it is generally okay to use simple HVAC as additional time involved in detailing out the HVAC system may not be justified. However, if the modeling is being done at advanced stages of building procurement, when the system details are available and are finalized, then detailed system modeling would typically be helpful. So beyond the design stage itself, during construction stages, it is recommended that whatever model you had at design is kept live and updated with the changes in decisions that would happen, for example, with value engineering. It should be at least be updated at the practical completion based on as constructed commissioning information so that upon handover, you have a model that fully aligns with the actual building. The model, that model can be used to fine tune the building during the initial years of operation and indicate remedial actions. So, regularly reviewing energy performance of any building once it's occupied is vital element in achieving and maintaining high levels of performance. In the coming years, post-occupancy evaluation is expected to become more commonplace. Post-occupancy evaluation allows holistic comparison of building performance with design stage intents and building targets to establish whether the building is performing as intended. This provides opportunities to identify shortcomings and enables their diagnosis and remediation for project teams to learn lessons for future. Modeling via use of calibrated models can be a vital tool to help in a robust building and systems evaluation after occupancy. Use of calibrated models, which I just mentioned as a part of post-occupancy evaluation and building retrofit projects has been detailed in different industry guidance documents, such as ASHRAE Guideline 14, IPMVP, and 6CTM63. These are, again, complementary guidance documents. 6CTM63 builds on the other two, especially regarding the use of model calibration as a part of systematic post-occupancy performance evaluation. This diagram from TM63 provides a procedural and replicable evidence-based methodology on how to create a calibrated model, which can be used for post-occupancy evaluation, diagnostics, performance issues, etc. This calibrated model process sits within the heart of a step-by-step measurement and verification framework, and which is there to quantify and identify root causes of building performance issues. So this is for the post-occupancy stage modeling use. So it's with Design Builder and with generally any modeling tools, it is fast and straightforward to update your model as the project evolves. So you could start with the simple compliance stage regulatory model and then develop it into early design stage model itself. And then you can use the same model post completion in calibration process for a simulation based post occupancy evaluation. There's actually a case study on Design Builder's website. Let me show you. So if you go to case studies, there's a case study here on using CIPSI TM54 and TM63 to accurately assess the performance of building using Design Builder. So this highlights how design stage performance model, which was developed before and then was used after calibration to undertake post-occupancy evaluation. So this is one thing I wanted to show you. Other resources that I mentioned during the webinar included initially a knowledge-based article on large models. So for that, if you can support a knowledge base on Design Builder website, then I just search for large models. And this is effectively the guidance document on this. And there are similarly useful general guidance as well on this in this website. And finally, the last thing I would like to show you, let me go to the design builder website again, is all the I've mentioned lots of existing webinars and content that was there on the various sequence of topics. So there's on the design builder website, you can go here and you can look at all the various modeling webinars. So this is the climate analytics one, and then I think there is one on modeling HVAC systems from simple to detailed, etc. So these are various things. You just open it up and it will um, show up, and you can view the recording of that. So that's that from me today.
Thank you, Nishesh. That was fantastic. A huge amount of information there and lots of really valuable resources. I just wonder if anybody has any questions. There was one earlier which I've responded to already to say we'll put some links on the YouTube recording as well. If anybody wants to follow up, including obviously to the Design Builder website. Are there any other questions that anybody wants to ask right now? I think you have blown everybody away with.
There's too much information.
I think it's just been so comprehensive, which is absolutely brilliant. So in that case, I will just move on very quickly to finish up with what's coming next. So the next webinars that we have are in January and March. They are part of the Urban Building Energy Modelling series. So one of the requests that we had in response to a question in previous webinars was for some more practical hands-on demonstrations of tools for UBEMS. So that's what's coming up, and we'll have a few more of those as well to add to that as we get the dates finalised. Our main focus for next year, for the first half of the year, is going to be a series on occupant-centric simulation-aided building design, and that's based on this book by that's edited by William O'Brien and Fahim Tamasebi, and we're going to be starting that series with a panel discussion to try and understand all your questions in advance and point you in the right direction. So we should be releasing the dates and the booking links for that next week, I hope. So do look out for that. The recording for this webinar will be on our YouTube channel, which is IBIPSA University. We've got recordings there from all the previous webinars as well. So it's an amazing resource of information about building simulation. A real, I think we now have around 50 videos there really covering all aspects of building performance simulation in really a lot of detail. So do have a look at that, check it out. If you're looking for some Christmas holiday viewing, do have a look. There's lots to keep you entertained there. Now, perhaps you are looking for a Christmas present for that special building simulationist in your life, and you're just stuck on what to get. Might I suggest that you get them a supporting membership for IBIPSA? Now, it may be something that you'd like to gift yourself as well, and our supporting members are incredibly important because they support the work of IBIPSA. They also get a subscription to the Journal of Building Performance Simulation, either online access only or a print subscription, and you get the right to use the IBIPSA supporting member logo. The fees for this are incredibly reasonable. These are pre-COVID prices. They haven't gone up at all. So it really is a great bargain for you. And you can find out more at ibipsa.org/membership. So with that, I'd like to thank you very much for joining us, and do please join us again soon for a future webinar. Thank you.